On the 4th of July, 1967, a small constellation of satellites drifted through high Earth orbit, listening for a kind of violence their makers feared above all others. They were called Vela, named for the Spanish verb vigilar, to keep watch, and they had been built for a single purpose. The world had signed a treaty forbidding the detonation of nuclear weapons in the atmosphere or in space, and the United States Air Force wanted proof, if proof were ever needed, that the treaty had been broken. To catch such a violation, Vela carried detectors tuned to the fingerprint of a bomb. A nuclear blast, even in the silent vacuum beyond the air, releases a blink of extraordinarily energetic light.
That light is called gamma radiation, and it is not the kind of light the human eye can see. It is shorter than X-rays, sharper than the ultraviolet, carrying enough energy in each photon to knock electrons loose from atoms and snap apart the molecules of living tissue. Gamma rays are the most piercing form of electromagnetic radiation the universe produces. They are the scream at the top of light's range. The satellites were designed, in other words, to be paranoid. They circled the Earth in pairs, spaced wide enough apart that the direction of any flash could be triangulated by comparing the arrival time of the signal at each detector. A blast in Siberia would register first at one Vela and microseconds later at another.
A blast in the South Pacific would register in a different order. With enough detectors in a wide enough ring, no nuclear test could hide. And then, on the 2nd of July, 1967, just 2 days before the American holiday for which history now pretends the instruments were quiet, 2 Vela satellites caught a flash that did not fit any pattern they knew. It lasted only a few seconds. It was extremely bright in gamma rays, and it came from a direction that made no physical sense, because when the analysts drew the line of its arrival across the heavens, it did not point at the Earth. It pointed outward, into the black. No one announced it. No one could.
The Vela program was a classified military project, and the anomaly was filed away to be studied by a small circle of cleared personnel. For several years, the flashes continued to arrive, one by one, always short, always sharp, always from impossible angles. They came from above and below, from the left and the right, from directions scattered across the sky without any pattern a Cold War engineer could decode. They did not cluster near any country. They did not cluster near the moon. They did not cluster near the sun. They did not seem to cluster near anything at all. For a while, the working theory among the cleared engineers was that the Soviets had found a clever way to cheat.
Perhaps they had tested a weapon behind the moon, and the gamma flash reached Earth by some reflected geometry. Perhaps they had tested a weapon in deep space, and the signal was leaking back. Perhaps the satellites themselves were defective, lighting up at random as their electronics aged in orbit. Every hypothesis was tried. Every hypothesis failed. The flashes kept coming. It is strange to imagine those rooms now, with their metal desks and their reel-to-reel tapes. The men in those rooms were looking for war. They were trained to expect mushroom clouds and betrayal. Instead, they were getting a message from no one, delivered from nowhere, in a language that had no rival power behind it. The messages were not in any code known to military cryptography.
They were not pointed at any target they could find on a map. They were simply there, blinking in the dark, unconcerned with the anxieties of a small planet and its quarreling nations. It would take years before anyone understood that what the Vela satellites had detected was not an act of war at all. It was the death of stars and galaxies so far away that their light had been crossing the universe for longer than the Earth had existed. Each of those tiny blinks was an event so violent that if you try to describe it honestly, your language begins to embarrass itself. The word explosion is not enough. The word catastrophe is not enough. Physicists would eventually settle on a more neutral and more accurate term.
They called them gamma-ray bursts. But in 1967, no one yet knew that. In 1967, they were simply the whisper in the wires, an anomaly waiting in a filing cabinet, a secret the universe had left on the doorstep of a planet too distracted by its own fear to understand what had arrived. There is a quiet lesson here, in the very first discovery. The deepest violence in the known universe reached us first through instruments built to watch our own violence. The cosmos did not wait for telescopes designed to look for it. It arrived unannounced, inside a spy satellite, while humans were busy suspecting one another. The darkness above us had been speaking all along.
It had simply been waiting for something that could listen, even by accident. The story of gamma-ray bursts, the story that the rest of this hour is going to tell, begins in that quiet strangeness. It begins with machines built for suspicion that stumbled, without meaning to, into wonder. It begins with a discovery no one could share. And it begins with a question that still has not been fully answered, even now, nearly 60 years later, as the satellites and the telescopes continue to catch the echoes of events so vast, so old, and so final, that our best physics still strains to hold them. What follows is the biography of the most luminous explosions in the universe. Lean back. Let your breathing slow.
The sky has always been like this. You simply did not know. Let us begin with a secret.
To understand what the Vela engineers were doing, it is worth remembering how frightened the world had become. By the early 1960s, the United States and the Soviet Union together possessed enough warheads to set fire to every city on Earth, and every ordinary citizen knew it. In 1963, exhausted by the nearness of annihilation, the two superpowers signed the Partial Test Ban Treaty. It forbade the testing of nuclear weapons in the atmosphere, underwater, and in outer space. Underground testing was still permitted, but above ground the skies were, at least in theory, to fall silent. The treaty depended on verification. Underground tests could be caught by seismometers. Underwater tests could be caught by the listening stations the navies had built for hunting submarines.
But outer space was different. No one had yet put up an array of instruments capable of catching a bomb detonated far above the atmosphere, where the hot light of a weapon could escape in every direction at once. So, the Americans built Vela. The program was enormous by the standards of its era, and most of it was hidden from public view. Between 1963 and 1970, a dozen satellites were launched in pairs into high circular orbits, more than 100,000 kilometers from the planet. From that height, each satellite could see almost half the sky at once, and together, properly spaced, they could see everything, all the time, every second of every day.
The instruments on board were specialized for catching the unmistakable signature of a nuclear detonation. A bomb makes a flash in visible light, but it also makes a flash in X-rays and gamma rays, and those are the frequencies that speak loudest against the quiet vacuum of space. A blast gives itself away in 3 stages. First, a pulse of neutrons. Then, a pulse of gamma rays. Then, a slower thermal afterglow. Vela was tuned to catch all 3. It was meant to be impossible to fool. And then, for several years, it began to fool itself. The first unambiguous gamma flash that could not be explained was recorded in July of 1967. It showed the gamma pulse, but not the neutron signature.
It showed the temporal profile of something powerful, but not the afterglow of a bomb. It seemed to arrive from the wrong direction. And then, months later, another flash came in, and then another, and then another, until the stack of anomalous events on the desks of the Los Alamos analysts was no longer small. The analyst who is remembered most clearly for noticing the strangeness of these signals was a young physicist named Ray Klebe-Sedel. He worked at Los Alamos National Laboratory, the place where the first atomic bomb had been designed. Klebe-Sedel was careful and patient, and he understood what a bomb was supposed to look like on a gamma detector. He also understood what a bomb was not supposed to look like.
And these flashes, whatever they were not that. Because the Vela program was classified, Klebe-Sedel could not simply publish his findings. He could not pick up the telephone and call the astronomy department at a university and ask if anyone had seen anything interesting. The information belonged to the Air Force, and it was reviewed slowly, carefully, and only within an approved circle. For several years, a discovery that would eventually reshape our understanding of the most violent events in the universe sat inside a safe, waiting for someone to decide that it was no longer a military secret. There is a peculiar double silence here. The first silence is the one the treaty was supposed to enforce. The absence of nuclear tests in the open sky.
The second silence is the one the classification forced upon the discovery itself. The inability to share the strange news with the astronomers who might have understood it. The universe had sensed something extraordinary, and even the small circle of humans who had caught it were not allowed to say so. Eventually, in 1973, the Air Force relented. Klebe-Sedel and his colleagues Roy Olson and Ian Strong published a paper in a journal called the Astrophysical Journal. The title was dry. The content was historic. They described 16 short, high-energy flashes that had been detected by the Vela satellites over the previous few years. Flashes whose origins could not be accounted for by any terrestrial or solar source.
They proposed, carefully and without overstatement, that these flashes came from somewhere in the cosmos. The paper did not use the phrase gamma-ray burst in its title. The phrase had not yet hardened. But within a few years, it would become the standard term, and every astronomy department on Earth would be trying to figure out what, precisely, was exploding. The first reactions in the astronomical community were a mix of excitement and suspicion. Some astronomers were thrilled by the idea of a new class of cosmic object. Others were skeptical, pointing out that the Vela instruments had been built for something else, that the detections could be artifacts, that the signals might come from within our own solar system. The debates at conferences were spirited. The data were thin.
For a while, almost any hypothesis was entertained, and yet the flashes kept coming, night after night, year after year. Other satellites, built later and pointed at the sky for astronomical purposes, began to catch them too. A Soviet mission called CONUS, launched in the 1970s, recorded hundreds of them. By the end of the decade, it was clear that whatever gamma-ray bursts were, they were not a rare event. The whole sky was peppered with them. On any given day, somewhere above the Earth, another one flickered in and out. But the big question remained untouched. How far away were they? Were they exploding in our own galaxy? Perhaps not very far from the Sun, in which case they would be merely fascinating.
Or were they exploding in galaxies so distant that our telescopes had trouble seeing the galaxies at all, in which case each burst would represent an almost unthinkable release of energy? The arguments about distance would last for more than 2 decades. It is one of the longest-standing controversies in 20th century astrophysics. It was not resolved by clever reasoning alone. It was resolved by a satellite, and by a second satellite, and by a stubborn refusal of the data to fit any simple model. The story of that resolution is the story of how the field grew up. But before we get there, consider what the first discovery really meant.
A network of spy instruments, built to catch the crime of war, had accidentally caught the death of stars. Those deaths had been arriving at Earth for all of human history. They had fallen through the canopies of carboniferous forests and over the sails of wooden ships, and no one had noticed, because we had no eyes for that kind of light. We built the eyes for our own worst fears, and through those eyes, for the first time in the history of our species, the universe showed us one of its most intimate secrets: the look of a star dying across half the visible cosmos. In the Cold War, we had watched the ground for enemies, and the seas for submarines.
Above all of that watching, something vaster was going on, unnoticed, in which we were neither the watchers nor the watched, but merely a small audience that had, almost by accident, been handed a ticket. We noticed, almost by mistake. And once we noticed, we could not look away.
By the late 1980s, the idea that gamma-ray bursts existed was no longer in doubt. The idea of what they were and where they were was something else entirely. Astronomers had 2 camps, and they disagreed with a vehemence that is difficult to describe unless you have spent time in the coffee rooms of a physics department. The first camp believed the bursts were local. That is, they believed the flashes came from objects relatively near the Sun. Perhaps neutron stars within our own Milky Way galaxy. Perhaps cometary bodies in the outer solar system being sucked into magnetic traps. If the bursts were local, their energy was modest.
A neutron star with a particularly strong magnetic field could produce them, and nothing about the physics would be especially new. The second camp believed the bursts were cosmological. That is, they believed the flashes came from galaxies billions of light years away,
at distances comparable to the size of the observable universe itself. If the bursts were cosmological, their energy was staggering. To be visible at such distances, each burst would have to release more energy in a few seconds than the sun will release in its entire 10 billion year lifetime. This was almost unimaginable. It suggested that the sky was occasionally lit, for a heartbeat, by the most violent events since the Big Bang.
Between these two camps, the difference in predicted energies was not 10 times, not 100 times, but something like 1 trillion times. The field was split by a factor of 10 to the 12th. It was not a small disagreement. It was not a matter of taste. Either gamma-ray bursts were mild and nearby, or they were among the most powerful events in nature, and the truth of the matter depended on a single unknown. How far away were they? To settle the question, astronomers needed a better eye. They needed a satellite with a wide field of view, sensitive enough to catch the bursts as they happened, and dedicated enough to record thousands of them in a single mission.
The instruments aboard Vela had been adequate for a military program, but they were not designed for deep science. The solution was a new satellite. It was called the Compton Gamma Ray Observatory, named for the American physicist Arthur Compton, who had won the Nobel Prize for discovering how gamma rays scatter off electrons. Compton the satellite was a monster of a machine. It weighed 17,000 kilograms at launch. It was the heaviest astrophysical payload that had ever been flown on a space shuttle. Its dedicated gamma-ray burst detector, called BATS, the Burst and Transient Source Experiment, consisted of 8 separate modules placed at the corners of the spacecraft, so that together they could see every part of the sky, not blocked by the Earth itself.
Compton was launched in April of 1991 from the Space Shuttle Atlantis, and it began almost immediately to change the field. The first few bursts that Bates detected were, by themselves, unremarkable. Each one was a short, bright flash, a few seconds long, with an energy profile similar to what the Vela satellites had seen years before. But as the weeks passed, and the flashes piled up in the BATSI database, and the data team began to plot them on an all-sky map, something began to emerge that none of the astronomers had expected. The bursts were evenly distributed. Not almost evenly. Not mostly evenly. Evenly. This was the single observation that broke the stalemate.
If the bursts were local, produced by neutron stars or other objects within our own Milky Way galaxy, they should have been concentrated along the plane of the galaxy, the bright band of stars that stretches across a dark night sky. The Milky Way is not a perfect sphere. It is a flat disk with a small bulge in the center, and nearly every class of object that lives in it is concentrated either in the disk or around the central bulge. If you map where the globular clusters live, you see a cloud around the center. If you map where the pulsars live, you see them in the disk. If you map where the nebulae live, you see them along the plane.
But if you map gamma-ray bursts, you see a completely featureless sphere. You see flashes here, flashes there, flashes in the north and the south, flashes in the direction of Andromeda, and flashes in the direction of nothing at all. The map shows the sky the way a child's pinprick drawing shows a ceiling. The dots are everywhere, with no discernible pattern.
There was only one natural explanation for this. The bursts were either very, very close, inside a spherical shell near the Sun, or they were very, very far. So far that the structure of our galaxy no longer mattered.
Either the bursts came from a cometary halo around the Sun, which would have been physically very odd, or they came from the deep universe. As the data accumulated, the nearby shell hypothesis grew harder and harder to defend. There was no known population of objects that should form such a shell. The cosmological hypothesis, on the other hand, had an immediate and satisfying implication. The universe is, on large scales, very nearly homogeneous. Looking far enough out in any direction, you see roughly the same density of galaxies. If gamma-ray bursts came from those galaxies, the sky map would indeed look like a featureless sphere. That was exactly what Botsey was seeing. By the mid-1990s, the cosmological interpretation was the leading hypothesis.
But it was still not a certainty. It is one thing to say that the bursts are probably far away. It is another thing to prove it. To prove it, you needed to identify the host galaxy of a single burst. You needed to say that flash came from that galaxy, and that galaxy is at that distance, and therefore that burst released that much energy. Botsey could not do this. Its position accuracy was not good enough. It could localize a burst to a patch of sky the size of a small quilt, but it could not point to a single galaxy within that patch. And by the time ground-based telescopes received the alert and swung to look, the flash was gone. Gamma-ray bursts lasted only seconds.
Once they were over, they were over. Or so it seemed. Some astronomers began to wonder, almost quietly, whether the bursts might leave behind a glow, a slower, softer aftermath in X-rays, or in visible light, or in radio waves. If such an afterglow existed, it might persist for hours or days after the gamma flash ended. If it persisted, you could chase it. You could point your optical telescopes at the rough patch of sky where the burst had been, and look for a fading star that was not supposed to be there. The search for the afterglow became one of the great hunts in late 20th century astronomy. For most of the Batesy years, it failed.
Sometimes a burst would occur, and optical telescopes would swing within a few hours. But the position errors were so large that the field of view included thousands of faint objects, any of which could have been the source. There was no way to pick the right one. The afterglow, if it existed, was hiding in plain sight. The breakthrough required a satellite that could pin down the sky position of a burst more precisely, more quickly, and in more than one wavelength. It required a satellite that could see the gamma flash and also see the X-ray afterglow and share that information with ground-based observers fast enough to matter. It required, in other words, the next generation.
By the time Compton ended its mission, in the year 2000, the field had matured. Thousands of bursts had been catalogued. The energy distribution had been studied. The durations had been divided into two broad populations.
short bursts under 2 seconds, and long bursts above. The sky was known to be isotropic, and the cosmological hypothesis was ascendant. Everything was in place for a definitive test. That test came, in the end, from a small Italian and Dutch satellite that almost no one outside the field remembers now, and whose name most people have never heard. But in April of 1997, that satellite did something the giant Compton Observatory, for all its 17,000 kilograms, had never managed.
And once
The satellite was called Beppo-Sax. The name is a small tribute. Beppo was the nickname of an Italian physicist, Giuseppe Occhialini, who had helped found the study of cosmic rays in the mid-20th century. SAX stood for Satellite per Astronomia Araghi X, Satellite for X-ray Astronomy. Beppo-Sax had not been built for gamma-ray bursts at all. It had been built to study the hot, high-energy skies of neutron stars and black hole binaries inside the galaxy. But its capabilities, by lucky chance, were exactly what the hunt for burst afterglows required. It carried 2 key instruments. The first was a wide-field gamma-ray camera that could see half the sky at once, tuned to the same energies that Botze had been monitoring.
The second was a narrow-field X-ray telescope that could be pointed with precision at a small region of the sky. The trick was simple in concept and difficult in practice. If the wide-field camera caught a burst, the spacecraft would turn, slewing through space, and point its narrow-field telescope at the same region. If there was an X-ray afterglow glowing where the gamma flash had been, the narrow-field telescope would see it. In the first months of its mission, Beppo-Sax caught several bursts, but for one reason or another, the follow-up did not yield a clean detection. There were pointing errors. There were delays. The afterglow, if present, faded too quickly. The team waited. On the 28th of February, 1997, a burst arrived that changed everything.
it was called GRB 970228, named for the date of its arrival in the Standard Convention. It was a long burst, about 80 seconds in duration, which meant there was time to react. The wide-field camera caught it. The spacecraft slewed. The narrow-field X-ray telescope pointed at the region of the sky where the flash had been, and there, fading slowly into the background, was a glowing spot that had not been there before. This was the afterglow. For the first time in human history, humanity had caught the lingering ember of a gamma-ray burst. Within hours, the Beppo-Sax team had refined the position down to a tiny patch of sky, much smaller than Botze could have managed.
The position was relayed to ground-based telescopes around the world. Optical astronomers at La Palma, in the Canary Islands, pointed their 4-meter William Herschel telescope at the patch and took a picture. Comparing that picture to archival images of the same field, they found a small fading point of light that had not been there before. It was the visible afterglow, and it was embedded. The images showed, inside a small, faint,
unremarkable galaxy, far from our own. Spectroscopy, the art of breaking the light into its component colors and reading the chemical and velocity information encoded there, was performed on the galaxy. It revealed a redshift.
The redshift is the way the expansion of the universe stretches the light of distant objects, making them appear redder than they would be at rest. The greater the redshift, the greater the distance. The galaxy hosting GRB 970228 turned out to have a redshift of about 0.7, which corresponded to a distance of several billion light-years. The numbers that followed made the old cosmological camp sit down very slowly. To appear as bright as it had appeared at the Earth, from a distance of several billion light-years, the burst must have released an amount of energy so large that if you wrote the number in kilograms of sunlight, the total would exceed the mass of a small star.
The burst had, in a few seconds, poured out the equivalent of several times the rest mass energy of the Sun, converting matter into radiation in a manner that no known stellar process could casually produce. And this was, as it turned out, only the beginning. A few months later, in May of 1997, Beppo Sachs caught another burst with another afterglow, GRB 970508. Its redshift was higher, about 0.83, putting it at an even greater distance. The energies, again, were extraordinary. Over the next few years, more and more bursts were caught and measured. The redshifts climbed.
One burst, GRB 980425, was associated with a supernova in a galaxy only 140 million light-years away, which was still astronomically distant, but, by the standards of the new data, almost local. Another, GRB 990123, came in with a redshift of 1.6, suggesting a distance of nearly 10 billion light-years. The sample of measured bursts kept growing. It grew into the tens, then the hundreds, then the thousands. Every burst with a measurable afterglow had a host galaxy. Every host galaxy was cosmologically far away.
Every burst represented a release of energy that summed across all the bursts in the observable universe, suggested that the deaths of stars were producing flashes visible across most of the volume of creation. There is a story in physics that the cosmological interpretation of gamma-ray bursts was not fully accepted by all astronomers until the afterglows began to come in. That is not quite right. The Botsy all-sky map had already persuaded most of the field, but the afterglows changed the matter from consensus to certainty. Once you can point to a galaxy and say, there, that one 3 billion light-years away, that is where it came from, the debate is over.
And when the debate is over, what is left is the question of what could possibly produce such energies. What is capable of releasing, in a few seconds, the energy of a small star? What can pour out, in a heartbeat, more light than 100,000 galaxies like our own? The answers would come slowly. They would require the next generation of satellites, such as the NASA mission called SWIFT, launched in 2004, which had been purpose-built for gamma-ray burst follow-up and could slew within a minute of a detection. They would require the Fermi Gamma-Ray Space Telescope, launched in 2008, which extended the energy range of the observations by orders of magnitude.
They would require, above all, the patient collaboration of thousands of astronomers across dozens of countries, working together in a global network that could, within minutes of a burst arriving at Earth, be pointing telescopes at the patch of sky from which it came. The answers, in broad strokes, would turn out to involve two distinct kinds of event, two distinct kinds of dying star, two distinct endings that the universe allows its most massive objects to choose from. One ending is long, the other ending is short. One ending comes from a single star, collapsing into itself with a violence that tears its own body apart. But the other ending comes from two stars, two compact remnants, falling together in a death spiral that ends in a kind of kiss whose fire is unlike anything else in nature. We will spend the next few chapters inside those endings. We will imagine the last minutes of a star about to collapse. We will imagine two neutron stars, each only 10 kilometers across, but each more massive than the sun, inching toward each other across a cosmic distance, losing their orbital energy to gravitational waves, until finally they touch, and for a single instant, the universe becomes brighter in their little corner than it has been since the first seconds of time.
But before we go there, let us stay for one more moment with the afterglow and with Beppo Sachs. There is something tender about small satellites that change everything. Beppo Sachs was not famous. It did not have the pedigree of Hubble. It was a modest Italian and Dutch collaboration, and yet this modest little machine caught, for the first time in human history, the dying ember of a star that had exploded before our planet had cooled. It turned a 25-year debate into a confirmed observation. After Beppo Sachs, the question of gamma-ray bursts moved from mystery to mechanism. We knew where they came from. The next question was how.
The longest gamma-ray bursts are the ones that announce themselves for minutes. By astronomical standards, minutes are nothing. But against the scale of a single flash of light, a minute is an eternity. A long burst can start with a soft, almost hesitant flicker, rise to a towering peak of emission, and then taper off in a series of smaller pulses. The whole sequence stretching across a span of time that feels, to the satellites watching, almost conversational. The dividing line between long and short bursts is traditionally set at 2 seconds. Bursts that last longer than 2 seconds are long.
This line is not completely sharp, and the two populations overlap at the boundary. But the statistical distinction is clear enough that every textbook agrees. Long bursts and short bursts are two different animals. The long ones, it turned out, are the dying breath of very massive stars. To appreciate what this means, you have to know a little about how massive stars live and die. A star is, in its essence, a long negotiation between two forces. Gravity pulls the star's matter inward, trying to crush it into a single point. Thermal pressure pushes outward, trying to fling the matter back into space. For most of a star's life, these two forces are held in near-perfect balance by the heat released from nuclear fusion at the core.
Hydrogen fuses into helium. Helium fuses into carbon. Carbon fuses into oxygen. Each step releases energy,
and the energy maintains the pressure that keeps gravity at bay. But fusion is not infinite. Eventually, the core of the star reaches an element called iron. Iron is the graveyard of nuclear fusion. Elements lighter than iron can fuse and release energy. Elements heavier than iron require energy to fuse. When the core becomes iron, fusion stops paying its own bills. The core cools, the pressure drops, and gravity, which has been patient for millions of years, finally wins. In most massive stars, the collapse of the iron core results in a standard supernova. The outer layers of the star explode outward. The core collapses into a neutron star, a remnant about 20 kilometers across, in which atomic nuclei have been squeezed against each other so tightly that the protons and electrons have merged into neutrons. The whole event releases about 10 to the 46 joules of energy, most of it in the form of neutrinos, with a small percentage going into the kinetic energy of the expelled gas and an even smaller percentage going into light. It is the brightest phenomenon in a galaxy. It is, by any ordinary measure, beyond comprehension. And it turns out, not quite enough to make a gamma-ray burst. For a gamma-ray burst, you need something more violent. You need a star whose core is so massive that, when it collapses, it does not stop at a neutron star. It continues. It continues past the limits of neutron matter. It continues until the gravity at the center becomes unconquerable. It continues until it becomes a black hole. The word collapser was coined for this kind of event. It describes the failure of a massive star to produce a clean supernova. The core collapses directly into a black hole without a successful rebound. The outer layers of the star, instead of being flung entirely into space, begin to fall onto the new black hole. Matter piles up in a spinning disk called an accretion disk. The disk heats to temperatures of millions of degrees. Magnetic fields tangle and wind.
And at the two poles of the new black hole, along its rotational axis, a pair of jets is launched, each narrower than a degree, each accelerated to speeds within a whisker of the speed of light. Those jets punch outward, through the falling stellar envelope, through the dying star's upper atmosphere, and finally, out into open space. When the front of a jet reaches the outer surface of the star and bursts into the surrounding medium, the energy carried in its relativistic flow is released in a torrent of gamma rays. The beam is narrow. The duration is long enough to reflect the continued accretion of matter onto the black hole, sometimes minutes, sometimes seconds, sometimes a sputtering sequence of pulses as the feeding slows and restarts.
This is the model that emerged in the late 1990s and early 2000s. It is called the collapser model, and it is now, broadly, the accepted picture for the origin of long gamma-ray bursts. There are variations. Not every collapser produces a successful burst. The jet has to survive the passage through the star. If the star is too big, the jet stalls. If the star has rotated too slowly, the jet never forms. The conditions required are specific. Statistics suggest that only a small fraction of core collapser supernovae produce a long gamma-ray burst. Most massive stars die without ever lighting up the full sky. But for the small fraction of stars that do, the conditions must be exquisite.
The star must be massive, probably more than 20 times the mass of the Sun. It must be rapidly rotating at its core, and it must have shed its outer envelope, leaving behind a naked helium or carbon-oxygen core, whose compact structure allows the jet to break free. Stars that meet all of these conditions are rare. Stars that meet all of these conditions and happen to have their rotational axis pointed at the Earth are even rarer. And yet, across the sky, at any given moment, somewhere, one of them is dying. The best evidence for the collapsar model comes from a small number of long gamma-ray bursts that have been observed simultaneously with supernovae.
The first of these, GRB 980425, was detected in April of 1998, relatively close by as these things go, at a distance of only about 140 million light-years. Within a few days of the burst, astronomers searching the galaxy at the burst's position found an unusually bright supernova, catalogued as SN 1998BW. Spectra of the supernova revealed it to be a type IC, the kind produced by a stripped-down massive star. The identification was strong. The connection was made. Here was a gamma-ray burst coincident, in time and space, with the death of a specific star. Further associations followed in the years afterward.
By the mid-2000s, nearly every long burst nearby enough to allow optical follow-up showed a supernova signature buried in its afterglow. The pattern was consistent. Long bursts were the deaths of very massive stars. The stars that produced them had been alive for only a few million years before dying. Their lives were short, flared and hot, and their deaths were among the most luminous events in the universe. To stand on a distant hypothetical planet and watch such a death would be to witness something that human language has never quite learned to describe. Imagine a star 50 times the mass of the Sun, burning so furiously that it will exhaust the fuel a sun-like star takes 10 billion years to burn in only a few million.
Imagine that star shedding most of its hydrogen atmosphere over tens of thousands of years, bathed in the winds of its own radiation pressure until only its dense helium and carbon core remains, spinning rapidly. Imagine the core reaching iron and the fusion stopping, and the central region beginning its fall. In less than a second, the inner core of that star falls in. A black hole forms. The outer layers, suddenly unsupported, begin to follow. The infall is not smooth. Magnetic fields, rotational energy, and the spinning geometry of the accretion disk conspire to launch two narrow jets at the poles of the newborn black hole. Those jets accelerate. They punch outward. They break through the surface of the dying star.
And when they do, the star has effectively become a lighthouse, sweeping a beam of gamma rays across the universe. From afar, the sight is almost unremarkable. A point of light, briefly brighter than the galaxy that contains it, flickers for a few minutes and fades. From close up, the sight is unsurvivable. Nothing within 10 parsecs of the axis could remain alive. Nothing within the path of the jet could remain in existence. The jet punches out of a star in a few seconds, but the star that produced it has been dying for millions of years. The conditions required for a successful burst have accumulated, drop by drop, across a span of time longer than mammals have existed on Earth.
And at the end of all that long preparation, in the span of a heartbeat, a light goes out that was visible from the other side of the universe. The deaths of the shortest-lived stars are sometimes the most extravagant. Stars are not, in this respect, very different from everything else.
For years, the short gamma-ray bursts were the stubborn cousins of the long ones. They shared the sky. They shared, very roughly, the same flash of light. They even shared, to a degree, the same places of origin, turning up in galaxies that were not obviously of a different population from the hosts of long bursts. But they would not fit the collapsar model. Their durations were too brief. Their afterglows were dimmer. Their host galaxies, on average, were not the same. Something else had to be producing them. The first hint of what the something else might be came from a careful look at the galaxies that hosted short bursts.
The long bursts preferentially appeared in galaxies that were actively forming stars, the kind of galaxies where massive short-lived stars are born and die in abundance. The short bursts appeared more evenly across all kinds of galaxies, including old elliptical galaxies in which almost no new stars had formed for billions of years. The implication was simple. Whatever made short bursts could happen in any galaxy, not just in the young, star-forming ones. Whatever made them did not require a newly born massive star. The leading candidate for decades was the merger of two compact objects, a pair of neutron stars orbiting each other in a binary system, slowly losing energy to gravitational waves, spiraling inward until they finally touched and merged into a black hole.
Or a neutron star and a black hole in a similar configuration, the neutron star being torn apart as it approached. Both scenarios predicted a burst of gamma rays with a duration of less than 2 seconds, preceded by a distinctive gravitational wave signal, and followed by an afterglow that would be dimmer than the afterglows of long bursts. The predictions sat on the shelves of theoretical papers for more than 30 years. It waited for direct evidence. It arrived in the most dramatic form imaginable on the 17th of August, 2017. That day, a gravitational wave signal swept through the detectors at the Laser Interferometer Gravitational Wave Observatory, known by its short name, LIGO, and through its European counterpart, Virgo.
The signal was named GW170817. It had the unmistakable waveform of two neutron stars spiraling into each other. It lasted about 100 seconds in the data, chirping upward in frequency as the two objects approached their final merger. And then, a second and 3/4 after the gravitational wave signal ended, the Fermi Gamma Ray Space Telescope recorded a short gamma ray burst from the same region of the sky. It was not a coincidence. The probability that a gamma ray burst arrived at that moment, from that direction, by chance was less than 1 in 10 million. The gravitational waves and the gamma rays had come from the same event.
For the first time in history, humanity had witnessed a cosmic event in two channels at once, in the stretching of space itself, measured by the mirrors of LIGO and Virgo, and in the flash of light that emerged a fraction of a second later from the point at which two neutron stars had finally kissed. The aftermath was a gift to the entire field of astrophysics. Within hours, the gravitational wave signal had been localized to a small patch of sky. Astronomers at the Las Campanas Observatory in Chile, using the 1-meter swope telescope, pointed at that patch and found a new, brightening object in a nearby galaxy called NGC 4993, only about 130 million light-years away.
The object faded over the following days and weeks, transitioning in color from blue to red. Its spectrum revealed the signatures of heavy elements being synthesized in the ejecta, elements like gold, platinum, and uranium. That detail is one of the most remarkable in the whole story of gamma-ray bursts. The merger of two neutron stars, it turns out, is where the heavy elements of the periodic table come from.
Not all of them, but many. The gold in a wedding ring, the platinum in a catalytic converter, the uranium in a reactor, these were created. The spectra confirmed in the last moments of two neutron stars that had been dancing around each other for billions of years before finally colliding.
When you wear a gold ring, you are wearing a small token from an event very much like GW 170817. Some neutron stars in some distant galaxy slammed together, and in the wreckage of that collision, atoms far heavier than anything ordinary stars can produce were forged and scattered into the interstellar medium. Billions of years later, those atoms were incorporated into the dust that eventually condensed into a young solar system. Some of them ended up in the crust of a planet that would later be called Earth. Some of them, much later still, ended up around your finger. Every piece of gold ever found by any human is, in some small way, shrapnel from a cosmic kiss.
But let us return to the mechanism of the short burst itself, which is no less astonishing than its jewelry. When two neutron stars in spiral toward each other, the last seconds of their approach are dominated by gravitational waves. These waves carry away orbital energy. The orbit tightens. The two stars, each about 20 kilometers across, sweep toward each other at speeds that become significant fractions of the speed of light. The final merger, when it occurs, is not gentle. It compresses the combined mass into a single object whose gravity is so strong that, almost immediately, it collapses into a black hole. During the last milliseconds before collapse, a small amount of matter is flung out of the system.
Tidal forces, disruption shocks, and the magnetic fields of the merging stars conspire to eject a pair of jets from the poles of the newborn black hole, just as in the collapsar model. The jets are narrow. They are fast. And when they punch into the surrounding medium, they produce a burst of gamma rays that lasts, typically, less than a second. Before the merger, the inspiral also produces a kilonova, a slower, softer flash of light in visible and infrared wavelengths, generated by the radioactive decay of the heavy elements freshly synthesized in the ejected matter. The kilonova is much longer lasting than the gamma burst itself. It can persist for days or weeks. It fades slowly, changing color as different isotopes decay into their daughter products.
The event that LIGO and Fermi saw in August of 2017 was only the first of its kind. Since then, more neutron star mergers have been detected in gravitational waves, and a handful have had associated electromagnetic counterparts. We are, as a species, newly able to watch the forging of elements in real time. The universe is cooperating with this new set of eyes. Every few years, another merger is detected. The sample grows. The physics sharpens. In the old picture, gamma-ray bursts were simply bright flashes of high-energy light.
In the new picture, they are signatures of the most intimate and final interactions in the universe. The moments when two of the densest objects in creation finally give themselves up to each other and become a single dark star. The word kiss is, of course, a human word. Two neutron stars do not share any of that softness. They are harder than anything we have ever touched, their crusts crystalline on scales no material on Earth approaches. When they touch, they do not flow into each other. They snap. They merge in a single convulsion, and in that convulsion, space itself trembles hard enough to be heard on planets 100 million light-years away. But still, in a broad sense, it is a meeting.
Two lives in long orbital courtship,
finally ending in a single object that is not either of them. The short gamma-ray bursts are, in the end, love stories. Love stories told by gravity, written in gold, read by distant astronomers who are only visitors.
There is one gamma-ray burst in particular that is worth spending time with. Its name is GRB 080319b. It arrived at the Earth on the 19th of March, 2008, at 6:13 Universal Time. It was detected first by the SWIFT satellite, which had been purpose-built for this work. SWIFT relayed the position to ground stations within about 40 seconds. Within 3 seconds after that, the Pie of the Sky telescope in Chile, a small robotic camera that had been scanning the sky, caught the optical afterglow. And within that brief window, the afterglow was already bright enough to see with the naked eye. That last sentence deserves to be read again.
The afterglow of GRB 080319b was bright enough to see with the naked eye. For a human standing in a dark place on Earth at the right moment, looking at the right patch of sky, the burst would have appeared as a fifth magnitude star, not remarkable in brightness, but present, visible, real. An ordinary star, about as bright as a faint star in a city-edge sky, lit up and then faded after a few tens of seconds. Anyone looking would have seen it. Almost no one was. The distance to the galaxy that produced it was later measured to be about 7.5 billion light-years.
That means that the star whose death this flash represented had died before the Earth or the Sun had formed. The photons had been crossing the universe for more than 7 billion years before finally striking the tops of our atmosphere and becoming a pinprick of visible light in a Chilean telescope. To put it differently, a star so far away that its light had been traveling for more than half the age of the universe had, for a few seconds, been visible to the unaided human eye. No other source in the universe has ever been measured to achieve that feat.
The total energy output of GRB 080319b has been estimated at about 10 to the 54 erg in its prompt emission alone, which is to say, in the few seconds of the burst itself, not counting the afterglow. 10 to the 54 erg is an amount of energy that does not fit inside any human intuition. It is equivalent to the rest mass energy of a body, roughly the mass of the sun being converted, in seconds, into gamma radiation. That is not how fusion works. That is not how any ordinary star works. That is the physics of something whose ordinary name is catastrophe.
For comparison, the Sun, over its entire 10 billion year main sequence lifetime, will radiate about 10 to the 51 ergs. GRB 080319b released roughly 1,000 times that amount in seconds. The ratio is almost impossible to hold in the head. It suggests that if you took the total light that the sun will ever produce from its birth to its death, multiplied it by 1,000, and compressed it into the span of a single breath, you would begin to approach the brightness of this one short event. And this one short event was not even the most extreme burst ever recorded. There have been others.
GRB 221009A, detected in October of 2022, has been nicknamed the Boat, the brightest of all time. It saturated gamma-ray detectors on multiple satellites. Its afterglow was followed for months across the electromagnetic spectrum. It was estimated to have been the brightest gamma-ray burst to strike the Earth in tens of thousands of years. Its apparent brightness was so extreme that particle detectors on the ground
recorded muons produced by its photons slamming into the upper atmosphere. The burst was at a distance of about 1.9 billion light-years, close by cosmic standards, and so bright that it disturbed the ionosphere of a planet on the opposite side of its arrival sky.
For the smallest moment of its appearance, a star's death, more than 1 billion years in the past, reached into the present and bent the signals of radio communication around the Earth. There is something almost tender about sitting with these numbers. The universe is full of extraordinary things. There are supernovae, there are quasars, there are accretion disks spinning around supermassive black holes. There are magnetars and pulsars and active galactic nuclei. All of these are, in their various ways, astonishing. But when an astronomer is forced to name the single most energetic class of event that occurs in the modern universe, the answer is almost always gamma-ray bursts. The bursts are, in the strict physical sense, the brightest things that have ever happened.
The brightness, of course, is not evenly distributed. The bursts are not balls of light, radiating equally in every direction. They are beams. They are jets. Their light comes out in narrow cones, pointing along the rotational axes of the black holes that produce them. If you are inside the cone, you see a gamma-ray burst. If you are outside the cone, you see nothing. This beaming is part of why the total energy figures are sometimes difficult to interpret. The apparent energy, calculated as if the burst were radiating equally in every direction, is an overestimate. The true energy, calculated taking the narrow beam into account, is smaller, but it is still, even corrected, enormous. The beaming is also why gamma-ray bursts are, from our point of view, rare.
Most bursts in the sky are not pointed at us. We only see the fraction whose jets happen, by chance, to be aimed in our direction. For every burst we see, there are probably 100 more bursts occurring in other parts of the sky, whose beams miss us entirely. The sky is secretly more violent than it appears. The part we observe is only the part that happens to be looking at us. This fact is worth sitting with for a moment. The most energetic events in the universe are also, almost by definition, the ones that are easiest to miss. A burst whose jet is a few degrees misaligned with Earth is invisible in gamma rays.
The same burst, the same dying star, the same explosion would have gone entirely unnoticed by our satellites. And if we somehow could see all the bursts, not just the small fraction aimed at us, the true event rate would be dozens of times higher. Somewhere in the sky, at any given instant, a star is dying in this extraordinary way, and its flash is passing us by, aimed at some other patch of empty space that does not have a civilization to notice. The sky is, in other words, buzzier than it looks. The bursts that reach us are the ones that share the narrow coincidence of our position and their geometry. We are a kind of accidental audience.
And yet, of course, even that accidental audience has had its share of extraordinary performances. The burst of March 2008, the burst of October 2022, the burst of February 1997, which handed us the first afterglow, the burst of August 2017, which handed us gravitational waves and gold. Each of these events was a single instant in the life of a single star,
and each one, by reaching our small planet at exactly the right angle, became an instant in the history of human science. It is as if the universe has been broadcasting in a code whose key we have only just discovered, and the messages that arrive have been chosen for us by the luck of our line of sight.
Luck or not, the messages keep arriving. Somewhere now beyond the northern horizon, or beyond the southern, a star that you will never see is in the last moments of its life, and if its axis is pointed anywhere near our direction, its death will flicker in a Fermi detector in a few thousand years. We will miss most of the violence of the universe. We cannot help it. Our planet is too small, and our time is too short. But we will catch some of it. And even the small amount we catch will be enough to teach us that the sky is not a quiet place. It is only a quiet-seeming place.
Underneath, at distances that give the ordinary mind vertigo, the largest deaths in existence are flaring again and again, and some of their light, every now and then, is landing on our faces. To understand why they can be so bright, it helps to remember the energy bookkeeping of the universe. Most of the energy that matters in astrophysics comes from 4 fundamental processes. Gravitational binding, in which the fall of matter into deeper potential wells releases energy. Nuclear fusion, in which small nuclei combine into larger ones and release a fraction of their rest mass as radiation. Nuclear fission and radioactive decay, in which heavy nuclei break apart. And the conversion of rest mass into radiation in the most extreme environments, most notably near black holes.
Stars, during most of their lives, run on the second process. Fusion is efficient, but it is not extraordinarily efficient. The fusion of hydrogen into helium in the sun's core, which is the process currently powering the light that falls on your skin, converts about 0.7% of the rest mass of the hydrogen fuel into radiation. That is a small percentage. It is, however, enough. The sun has, in its 4.5 billion years of life, converted about 100 Earth masses of hydrogen into helium, radiating the energy difference across the solar system and keeping the planets warm enough to permit the development of things like lungs and conversations. A supernova is more efficient.
The collapse of a massive stellar core releases about 10% of the rest mass of the collapsing material as energy, most of it in the form of neutrinos. Only a small fraction of that energy becomes visible light. Most of it leaves the star in a burst of neutrinos so vast that, for a brief moment, a single supernova outshines its entire galaxy in neutrinos alone. A gamma-ray burst, if our models are correct, taps an even deeper source. The accretion of matter onto a newly born black hole, combined with the extraction of rotational energy from the black hole itself, can convert up to 40% of the rest mass of the accreted material into outflow energy.
Of that, a small fraction ends up as electromagnetic radiation, and most of the electromagnetic radiation is in gamma rays. But even a small fraction of 40%, when applied to the mass of a stellar core, is a colossal figure. Here is one way of comparing it. The Sun, in all of its 10 billion years, will radiate about 4 times 10 to the 51st ergs of energy. A typical long gamma-ray burst releases, in its prompt gamma emission alone, about 10 to the 52 or 10 to the 53 ergs. The extreme events, such as GRB 080319b can reach 10 to the 54.
That means a single gamma-ray burst in a few seconds releases more electromagnetic energy than the sun will release in 10 billion years. By some accounts, a single bright gamma-ray burst releases more energy as light than 100 average stars will produce in their entire lives. If the whole of a star's life, from its birth in a molecular cloud to its final collapse, were compressed into a ball of stored energy, the light it would produce if that ball were released in a single second would still fall short of what a bright gamma-ray burst does, naturally, on a random Tuesday. There is a kind of economic cruelty to this, from the perspective of the star.
A star spends its entire life carefully budgeting its nuclear energy, keeping its balance against gravity for ages. And then, in the final second of its existence, it throws away everything it has saved, plus more, in a single pulse of light. It is as if the star had been saving every cent of its salary for 10 billion years, and then, in the last heartbeat of its life, spent the entire savings and its body on a single firework. Stars, of course, do not plan. The compression happens because the physical conditions force it. Still, there is something in the pattern that is easy to mirror from within a human life. For the universe at large, the brightness of a gamma-ray burst matters for another reason.
These flashes are so luminous that they are visible at cosmological distances across most of the observable volume of the universe. They can be used, in principle, as beacons to light up the regions between galaxies, where gas clouds and distant structures absorb some of their photons and leave chemical fingerprints in the burst's afterglow spectrum. A single bright burst can tell astronomers not only about the star that produced it, but also about every piece of cosmic matter between that star and us. For this reason, gamma-ray bursts are being used as probes.
In the same way that a flashlight can reveal the insides of an attic, a bright burst can reveal the insides of an intervening galaxy, or the distribution of ionized hydrogen in the early universe, or the composition of gas clouds billions of light years away. The burst at GRB 080913, for instance, occurred at a redshift of 6.7, placing it in an era when the universe was less than 1 billion years old. Its light had traveled through the reionization of cosmic hydrogen. Its afterglow spectrum contained features imprinted by that process. Its death was a lantern carried back in time. In this way, the deaths of the most massive stars help us understand the universe. They are the brightest things.
They are therefore the things we can see the furthest. They are the flashlights by which the cosmos, on occasion, consents to illuminate itself for us. And in the process, they remind us of something we can sometimes forget. The ordinary light of the daytime sky, the familiar glow of the sun, is only the quiet end of a much louder spectrum. The sky is ringing, all the time, with signals many orders of magnitude more intense than anything we naturally perceive. Our eyes are tuned to a narrow window of photon energies. Even within that window, we see only a tiny slice of the brightness that is out there.
If we had eyes that could see gamma rays, the night sky would not be the familiar still pond we have imagined for so long. It would be a pan of dark water, dotted every few minutes, with tiny, fleeting sparks. In the course of an evening, you would watch dozens of stars elsewhere in the universe die. You would see the kind of violence that leaks through the sky when our usual filters are lifted. You would never quite look at the stars the same way again. Our ordinary darkness is a merciful edit. The raw footage is not calm.
Perhaps the most important thing to understand about a gamma-ray burst, for anyone interested in whether it might ever concern us, is that it is not a ball of light. It is a beam. When a star collapses into a black hole and launches its jets, those jets do not spread out into the sky. They are narrow. Their opening angle is typically only a few degrees, sometimes less. The energy of the burst is concentrated along two axes, one at each pole of the rotating black hole. The rest of the sky, around the star, receives a small fraction of the total energy, and only after considerable mixing with the surrounding matter.
If you imagine the burst as a lighthouse, the beams are the pair of bright cones, and the rest of the sky is the dark hemisphere outside them. A ship in the direct line of a lighthouse beam will see a dazzling light. A ship to the side of the beam will see only the faint scattering that reaches it through the air. A ship behind the lighthouse will see almost nothing. The geometry of a gamma-ray burst is exactly like this, except that the lighthouse is a dying star. The beams are relativistic jets of matter and light, and the ships are entire star systems, galaxies, or civilizations scattered through the universe around the source.
For any given burst, only the systems that happen to lie within the narrow cone of the beam receive the full intensity of the event. Every other system simply gets a much milder light show, a bright supernova perhaps, or a flash of X-rays, but nothing like the skin-melting pulse of gamma rays that a directly aligned observer would see. This is profoundly important for the question of Earth's safety. The narrow beam means that most gamma-ray bursts, even those in our own galaxy, would not directly affect us. For a burst to pose any real danger, its jet would have to be pointed at Earth, not mostly in our direction, not approximately in our direction, precisely in our direction.
The opening angle of a typical gamma-ray burst jet is about 3 to 5 degrees. If you imagine a cone of that angular width extending outward from a star in some direction, the area it sweeps across the surface of a sphere at a distance of, say, 1,000 light-years is a very small fraction of the total sphere. Most directions from the point of view of the star are not aimed at us. Only a tiny slice is. The odds that any given burst in the galaxy has its jet aimed at Earth are therefore small. The odds that a burst close enough to pose a danger also has its jet aimed at Earth are even smaller.
And the odds that we are unlucky enough to be in exactly the right spot at exactly the right time for such an event are, across any human lifetime, astronomically remote. That does not mean the odds are zero. Consider what happens to a star system that is inside the beam of a nearby gamma-ray burst. The jet is moving at a velocity within a hair's breadth of the speed of light. It is carrying kinetic energy equivalent to a significant fraction of the mass of a small star. When it collides with the interstellar medium in the vicinity, it produces the gamma flash we observe from afar. When that gamma flash travels through space and reaches a planet inside the beam, the effects are not subtle.
If a gamma-ray burst occurred within, say, 1,000 light-years of Earth, and its jet happened to be aimed directly at us, the consequences would be severe.
The gamma radiation reaching the upper atmosphere would deposit its energy there, not at the surface. Gamma rays are absorbed by the air, which is, in this case, a small mercy. But the absorption itself is catastrophic because it transforms the upper atmosphere on the day side of the planet into a shell of ionized gas at temperatures that would briefly rival the chromosphere of the sun. The shock would not kill animals directly. The gamma photons themselves would not reach the ground in any meaningful numbers, but the atmosphere would be transformed.
Oxygen and nitrogen molecules, normally stable companions in the air we breathe, would be broken apart. The reactive fragments would recombine, not into ordinary molecules, but into a pall of nitrogen oxides. These oxides would catalyze the destruction of the ozone layer. The shield that currently protects the biosphere from the sun's ultraviolet radiation would thin substantially, and in some models, for some burst distances, might be lost almost entirely. What follows the loss of the ozone layer is not a dramatic flash of fire, but a slow, grinding biological disaster. The ultraviolet radiation of the sun, normally filtered by atmospheric ozone, would begin to reach the surface at intensities lethal to most microscopic life. Phytoplankton in the upper layers of the ocean, the foundation of nearly every marine food chain, would be heavily damaged. The base of the biosphere's pyramid would collapse. The organisms that feed on phytoplankton would starve. The organisms that feed on those would starve. Within years, the ocean would empty of its biological productivity, and the chain would propagate upward through every predator layer, until eventually, even the apex consumers would begin to fail. On land, the effects would be slightly different, but no less severe. Increased ultraviolet would damage crop plants, reduce photosynthetic efficiency, and generate mutations in every population exposed to sunlight. Mass extinction would not occur because of the gamma flash itself. It would occur because of the slow unraveling of the food web that the flash had initiated. This scenario is not science fiction. It is the result of careful modeling. It is also, some scientists have argued, a candidate explanation for one of the mass extinctions in Earth's own deep past. We will come to that in a later chapter. But for the present chapter, the point is this. A gamma-ray burst does not have to hit the Earth to be dangerous. It only has to point at the Earth. The beam is the weapon. The distance is the detail.
And the beam is narrow, which is why, across the long history of the Earth's biosphere, no such event has, so far as we know, happened so strongly as to erase life entirely. Of the bursts that occur in the galaxy every several 100,000 to million years on average, only a small fraction have their jets pointed in our direction at any given moment. Of those, only the closest could cause serious damage. Even when one does, the biosphere, battered and thinned, has the capacity to recover if enough time passes before the next event. Life on Earth has been, in this respect, extraordinarily fortunate. For 4 billion years, the cumulative exposure to cosmic radiation has been survivable.
The biosphere has ridden out whatever gamma bursts have happened to align with our position. Whether this is because of the narrow beams, or because of the rarity of bursts in our corner of the galaxy, or because of pure chance, is a question we cannot fully answer. But we are here, having this conversation, because the long statistics have, up to now, treated us gently. There is a kind of humility that comes with understanding this. Every living thing on Earth is currently sitting inside a statistical window that has, so far, been narrow enough to let our chemistry continue. The window has no guarantees,
It simply is. The odds favor continued survival, by a wide margin, over any human-scale time frame. But the odds are not unity. And the universe is, in its overall geometry, a place in which beams of extraordinary energy are sweeping through, at random angles, at a steady cosmic rate. We are, without being asked, a small target. We will, without being asked, remain so. It is one of the quiet facts of being a terrestrial animal in the 21st century. It is not a fact that should keep anyone awake. It is, however, a fact worth knowing in order to appreciate more fully the small mercy of each ordinary day. The sky above you, even now, as you lie there with your eyes softening towards sleep, is crisscrossed by beams, whose geometry is almost never pointed at you. The almost is what keeps the biosphere alive.
The nevers of the past have been our fortune. The futures remain to be seen.
Let us, for a while, move from the general to the specific. There is a star in our galaxy that is worth knowing about. It is not bright to the naked eye. You cannot see it without a telescope and a good chart of the southern sky. Its catalog name is Wolf-Rayet 104, usually abbreviated WR104. It lies about 8,000 light-years from Earth in the constellation Sagittarius, in a region that points approximately toward the center of the Milky Way. WR104 is not a single star. It is a binary system, two stars orbiting each other at a distance so close that their outer atmospheres nearly touch.
The primary star is a Wolf-Rayet, an old, stripped-down giant that has lost most of its hydrogen envelope in a lifetime of violent stellar winds. It is now a naked helium core, burning furiously, hot enough that its surface is more than 100,000 degrees. Its mass, best estimates suggest, is somewhere between 10 and 20 solar masses. Its age, by stellar standards, is nearly over. It is, in astronomical terms, within a few 100,000 years of the end of its life. The secondary star is an OB-type star, younger, still in the middle of its hydrogen-burning life, less evolved. It orbits the Wolf-Rayet every 241 days.
The two stars together from Earth look like a single point of light, but the subtle spectroscopic changes as they orbit reveal their dance. What makes WR104 famous is not its mass, not its age, not its spectrum. It is a structure of dust that wraps around the binary pair like a pinwheel. Infrared imaging, taken by the Keck telescope on Mauna Kea in the 1990s and improved in subsequent observations, has resolved the system into a beautiful, clockwise turning spiral of dust, blown out from the colliding stellar winds of the two stars. The spiral is one of the cleanest images in all of stellar astronomy. It is almost circular, almost perfectly symmetric. And its near-perfect circularity reveals something important.
The rotational axis of the binary system is, from our perspective, pointed almost directly at us. Or at least, that is what early images suggested. If the axis is pointed at us, and if the Wolf-Rayet primary eventually explodes as a collapsar, and if that collapse produces a gamma-ray burst whose jet is launched along the axis of the binary, then the jet would be pointed at Earth. The distance, 8,000 light-years,
would be close enough that the gamma flash would deliver an enormous dose of energy to the upper atmosphere. This combination of facts, when it was first noted in the early 2000s, caused a small stir in the astrophysical community.
For a while, WR-104 was referred to, only half in jest, as the gun pointed at Earth. More recent observations have softened the concern slightly. Higher resolution images, taken with the W.M. Keck Observatory in later years, have suggested that the inclination of the system is not quite as face-on as it first appeared. The best estimates now place the rotation axis somewhere between 0 and 30 degrees from our line of sight. That is still relatively close to being aimed at us, but it is not perfectly aimed. The jets of gamma-ray bursts, as we noted, have typical opening angles of 3 to 5 degrees.
For WR-104's jet to strike Earth directly, the axis would have to be aligned within that narrow cone. 30 degrees, if the later estimates are correct, is well outside that cone. At 30 degrees, the jet would miss the Earth by a wide margin, and even if a gamma-ray burst did occur, the direct effects on the planet would be mild. But the geometry of WR-104 is still not known with perfect confidence. Different observing techniques yield different values for the inclination angle. Some models suggest the dust spiral's geometry is a good proxy for the binary's orbital plane. Others suggest it is not. There is enough uncertainty that the question remains, in the literature, open.
There is also the question of whether WR-104 will produce a gamma-ray burst at all. Not all Wolf-Rayet stars end their lives as collapsars. Many of them simply produce a type IC supernova, without the necessary combination of core mass and spin to launch a relativistic jet. Whether WR-104 has the right properties depends on details of its current evolution that are hard to measure from 8,000 light-years away. Even if the star does produce a gamma-ray burst, the timing is uncertain. Wolf-Rayet stars are near the ends of their lives, but nearness, in stellar terms, can mean anywhere from a few thousand to a few 100,000 years. The star might explode tomorrow. It might explode in 500,000 years.
8,000 light-years away. We would not see it happen until 8,000 years after the event itself, given the light travel time. In other words, if WR-104 exploded today, we would not know for another 8 millennia. Conversely, if it had exploded 8,000 years ago, the flash might arrive on Earth next week. Let us sit with that thought for a moment. The light from WR-104 that you would see through a telescope tonight, if you pointed a telescope at Sagittarius and found it, is light that left the star 8,000 years ago. At the time that light was leaving its surface, the Neolithic revolution was underway on Earth. Agriculture was taking root. The first permanent villages were forming.
The Egyptians had not yet built their pyramids. The Chinese had not yet developed writing. The light you see now is older than most human civilization. The star whose light that is might by now already have died. We would not know. The news is in transit. It will reach us when it reaches us. If the news ever reaches us in the form of a gamma-ray burst, the effects on Earth depend heavily on the geometry. In the worst case, with the jet aimed directly at us, the consequences could be similar to those described in the previous chapter: ozone depletion, ultraviolet damage, biosphere stress.
In the most likely case, given the updated inclination estimates, the jet would miss Earth, and we would see only a bright supernova, dramatic but not catastrophic. Some astronomers have argued that WR104 has received more attention than it deserves, that the early suggestions of its alignment were based on incomplete data, that later observations have reassured the field. Others have argued that the uncertainty is still large enough to justify concern. The debate is ongoing, and neither side can be fully confident without better data. What we can say is this.
Of the stars we know of in our galaxy that are candidates for producing a gamma-ray burst within the next several 100,000 years, and that might be aligned in our direction, WR104 is the most discussed. It is not the only candidate. There are others, but it is the one whose geometry, whose age, and whose stage of evolution combine to make it a topic of lasting interest. Thinking about WR104 is a good exercise in cosmic humility. Here is a star sitting in exactly the same patch of sky it has occupied for millions of years, doing exactly what it was going to do anyway, while our species has been inventing telescopes and treaties and the concept of risk.
The star does not know it has been studied. It does not know that a small civilization on a small planet 8,000 light years away has, for a few years, called it a gun. It simply burns. It will burn until it cannot. And when the time comes, it will die, in the way massive stars die, without any opinion about who is watching and from where. The stars are not angry at us. The stars are not paying attention at all. Physics has no grudge. Physics only has rules. WR104 will either explode with its jet aimed at us, or it will not. The odds, as best we can estimate, are against a direct hit. We will probably never know what the star chose.
We will probably only ever know what happened to us. In the meantime, the star burns. Its winds continue to blow. Its dust continues to spiral outward in its beautiful clockwise pattern, which we admire through our telescopes, and which has become, for reasons neither the star nor the dust can be responsible for, a topic of human contemplation. A pinwheel of glowing dust, silently spinning 8,000 light years away, has become, for a moment, part of the mental furniture of our species. That too, in its quiet way, is something astonishing.
There is a moment in the history of life on Earth that happened long before any mammal walked on land, before any fish crawled onto a muddy beach, before the continents had assumed any of the familiar shapes that we teach children in atlases. It happened about 444 million years ago, at the end of a period of Earth's history called the Ordovician. The Ordovician was a strange time to be alive. The planet looked unfamiliar. Most of the land mass was concentrated in a single supercontinent called Gondwana, which stretched across the southern hemisphere and included pieces of what would later become Africa, South America, Australia, India, Antarctica, and Arabia.
The northern hemisphere was largely ocean, with a few scattered land masses that would later become Laurentia, Baltica, and Siberia. The oceans were vast, shallow, and teeming with life, but that life was not life as we would recognize it. There were no land plants, at least none that had established a robust ecosystem. The land was barren, rocky, and occasionally patched with small mats of microbial mats, and perhaps a few ancestors of mosses. The oceans were vast, shallow and teeming with life. But that life was not life as we would brocking maker waifs.
A diverse, complex ecosystem, older than anything alive on land today, had been building itself for tens of millions of years. And then, in geological terms, very quickly, much of it died. The Ordovician-Silurian extinction event, as the boundary between these two periods is known, is one of the 5 largest mass extinctions in the history of multicellular life. It is often ranked second in severity, behind only the end, Permian extinction, 200 million years later. Somewhere around 85% of marine species went extinct. Whole orders of life vanished from the fossil record. The reefs emptied. Then, in geological terms, very quickly, much of it died. The Ordovician-Silurian. The ocean. The extinction event seems to have occurred in 2 main pulses, separated by a few million years. The first pulse coincided with a rapid cooling of the planet. Massive glaciers formed over Gondwana, which by that time had drifted over the South Pole. Sea levels dropped by dozens of meters as water was locked up in ice. Shallow marine habitats, which had been home to the majority of Ordovician species, dried out. The organisms that depended on them suffered immediate local extinctions. Then, a few million years later, the glaciers retreated, and sea levels rose again, and the warm-adapted species that had survived the first pulse began to die in a second pulse of extinctions, perhaps because of changes in ocean chemistry or oxygen levels.
For most of the 20th century, the most widely accepted explanation for the Ordovician extinction focused on this glacial event. The climate had cooled, the oceans had retreated, the shallow seas had vanished, and the life that had depended on them had not had time to adapt. The glaciation, in turn, was attributed to some combination of continental configuration, volcanic activity, and the depletion of atmospheric carbon dioxide. In the year 2003, a team of astronomers and geologists proposed something different. In a paper published in the journal Astrobiology, led by Adrian Malott at the University of Kansas, and including colleagues from multiple institutions, the team argued that a nearby gamma-ray burst might have initiated the Ordovician extinction.
Their argument was based on a combination of modeling the ozone depletion effects of a short, intense gamma burst and examining the fossil patterns of the first pulse of the extinction. The key observation was this: the first pulse of the Ordovician-Silurian extinction affected marine organisms in a depth-dependent pattern. Surface-dwelling and shallow-water species were hit harder than deep-water species. This pattern is consistent with a sudden increase in ultraviolet radiation at the ocean surface, which would damage phytoplankton and the shallow-water organisms that fed on them, while leaving deeper-dwelling species relatively protected by the overlying water column. A gamma-ray burst aimed at Earth would, as we saw in an earlier chapter, deplete the ozone layer.
After the ozone depletion, ultraviolet radiation from the sun would reach the surface in unusually high doses. Phytoplankton would be damaged. Shallow water food chains would collapse. Deep water organisms, protected from surface UV by the water column, would fare slightly better. The Malott paper pointed out that this pattern of greater impact on surface and shallow water species is exactly what the fossil record shows. The authors calculated that a gamma-ray burst at a distance of around 6,000 to 14,000 light-years, with its jet pointed at Earth and delivering an energy density consistent with typical long gamma-ray bursts, could have produced the observed pattern. The glaciation that followed, they speculated, might have been a delayed consequence of atmospheric chemistry changes initiated by the burst. The hypothesis is elegant.
It explains a puzzling pattern in the extinction data. It provides a specific, falsifiable mechanism, and it connects the death of a star in our galactic neighborhood to the death of much of the Ordovician biosphere. It is also, it must be said, speculative. The evidence for a gamma-ray burst trigger is indirect. It rests on a statistical correlation between expected effects and observed patterns, not on any direct tracer that could confirm a specific event in the distant past. Other explanations, such as oceanic anoxia, volcanic activity, or purely climatic causes, remain viable. Most paleontologists today consider the gamma-ray burst hypothesis an interesting possibility, worth taking seriously, but not established. Still, it is worth dwelling on the implications.
If the hypothesis is correct, then somewhere in the galaxy, about 444 million years ago, a star died. It was probably a Wolf-Rayet, or a similar massive star in the final stages of its life. Its core collapsed. A black hole formed. 2 jets of relativistic matter and radiation were launched from its poles. By accident of geometry, one of those jets was aimed at Earth. The light from that star's death crossed the intervening space for thousands of years. It arrived without warning. The gamma rays were absorbed by the upper atmosphere. The air heated. Nitrogen oxides formed. The ozone layer thinned. Over the following months, ultraviolet radiation from the sun penetrated deeper into the atmosphere and oceans than it had before.
Phytoplankton died in great numbers. The oxygen content of the surface ocean dropped. Entire food chains began to stagger and fall. The animals alive at the time would not have known what was happening. A trilobite does not have the capacity to understand the death of a distant star. It simply would have found its environment becoming inhospitable. Fewer small organisms in the water, less to eat, more damage from sunlight, less comfortable temperatures. Over the course of generations, populations would have declined. Species would have vanished. The burst itself might have lasted only a few seconds. Its effects would have propagated through the atmosphere, the oceans, and the biosphere for tens of thousands, perhaps millions of years, as the climate and ecosystems rearrange themselves around the new conditions.
If this is what happened, then the Ordovician extinction was, in part, a casualty of a story that began in a distant corner of the galaxy, in a star that never knew about the ocean, the trilobite, or the atmosphere it would eventually disturb. A star that burned out its fuel in a normal stellar life, collapsed and, without any intention, without any opinion, ended many millions of lives that were neither its relatives nor its neighbors. There is something strangely lonely about imagining this. Whole species of trilobites, with their delicate eyes and intricate exoskeletons, disappearing under a sky that seemed at the time no more eventful than any other.
A mother nautiloid glimpsed through the Silurian water column, unaware that the sky had been briefly altered by a death 3,000 parsecs away. If the Ordovician hypothesis is correct, then the largest single episode of life lost in any non-impact, non-volcanic event in the Paleozoic was caused by a star, not by climate, not by volcanism, not by the vagaries of oceanic chemistry, but by a single, specific, nameless point of light that appeared briefly in a Silurian night sky and then faded, leaving behind it only an invisible chain of chemical events that would, across the following centuries, reshape the map of life on Earth. This is not a cheerful thought. It is, however, an honest one. The biosphere has survived many things: asteroid impacts, volcanic winters,
supercontinental formations and breakups, ice ages, greenhouse climates. If the gamma-ray burst hypothesis is right, it has also survived at least one direct cosmic shooting. 85% of marine species did not make it through that event, but 15% did. And from that 15%, the Silurian and Devonian biospheres eventually regrew. Reefs rebuilt. New families of corals evolved. The first plants climbed onto the land. Life, in other words, is stubborn. Even when a star fires at it directly, it does not die entirely. It contracts. It adapts. It waits. And then, in the fullness of geological time, it fills the niches again, with new occupants who have never heard of the old ones. Whatever happened to the Ordovician, the story was not the end of the story.
It was only a chapter in a much longer book, one that we, in our very recent way, are now reading backward, trying to figure out what the earlier paragraphs said. It is quite possible that one of those paragraphs was written.
Among all the scales on which gamma-ray bursts can be understood, perhaps the most important one for us is the scale of the Earth's atmosphere. It is easy to overlook the atmosphere. We breathe it without thinking. We watch it turn from blue to orange at dusk without dwelling on its composition. We rarely consider that the entire mass of breathable air on Earth, gathered together, amounts to roughly 5 × 10 to the 18th kilograms. A large number by human standards, but a tiny number compared to the mass of the planet itself. The atmosphere is about 1/1,000,000th of the Earth's total mass. It is, in geological and planetary terms, a thin shell. Imagine the Earth as a peach.
The atmosphere, scaled down accordingly, is only about the thickness of the peach's skin. That thin skin does almost everything. It distributes heat from equator to pole, through winds and ocean air exchange. It moderates the temperature of the surface so that it remains habitable. It protects the surface from solar ultraviolet radiation via the ozone layer at altitudes between about 15 and 30 kilometers. It absorbs and dissipates the kinetic energy of incoming meteoroids, turning most of them into harmless flashes in the night sky. It shields us from charged particles in the solar wind with the help of the Earth's magnetic field. It allows the acoustic and biochemical signals of life, like the voice you are listening to right now, to propagate.
When a gamma-ray burst is pointed at Earth, the atmosphere is the first line of defense and the first place where things go wrong. The photons from a gamma-ray burst do not reach the ground directly. Gamma rays interact with air molecules through Compton scattering, pair production, and photoelectric absorption. Each of these interactions converts a high-energy photon into lower-energy particles, or photons, which themselves interact with further atmospheric material. The net result is that the gamma rays are absorbed within the upper atmosphere, mostly above an altitude of about 40 kilometers. The surface of the Earth receives almost no direct gamma flux, but the absorption itself is the problem. When the upper atmosphere absorbs the gamma-ray pulse from a nearby burst, it is flooded with energy.
The absorbed radiation heats the gas, ionizes atoms, and breaks apart molecules. Atmospheric nitrogen, which is by volume about 78% of the air, and in ordinary conditions extraordinarily unreactive, becomes suddenly reactive. Oxygen, likewise. The ionized and reactive fragments recombine into new species, chief among them nitrogen monoxide, nitrogen dioxide, and other nitrogen oxides collectively abbreviated as NOx. These nitrogen oxides are the problem. Nitrogen oxides, in the upper atmosphere, are catalysts for the destruction of ozone. A single molecule of nitric oxide can destroy hundreds of ozone molecules before being removed from the atmosphere by slower transport processes. Ordinarily, nitrogen oxides are rare in the upper atmosphere because the energy required to break nitrogen and oxygen apart is large.
But a gamma-ray burst in seconds provides that energy in abundance. Nitrogen oxide levels rise sharply, and wherever nitrogen oxide rises, ozone falls. The destruction of ozone is not immediate and global. It propagates over months to years, as the newly formed nitrogen oxides are transported by atmospheric circulation, and as they react with ozone wherever they are carried. The northern and southern hemispheres might experience different levels of depletion, depending on the exact timing and latitude of the initial energy deposit. But across the planet, over a period of years, the ozone layer becomes thinner and patchier than it would otherwise have been. The thinner ozone layer allows more ultraviolet radiation from the sun to reach the surface.
Biologically effective ultraviolet, or UVB, is the portion of the solar spectrum most responsible for damaging DNA. Under normal conditions, almost all UVB is absorbed by stratospheric ozone before it can reach the surface in dangerous quantities. With the ozone layer depleted, UVB floods the surface environment. Humans would not, in a typical scenario, die directly from this ultraviolet exposure. But we would suffer. Skin cancers would rise. Cataracts would become more common. Immune suppression from UV exposure would make infectious diseases more serious. Agricultural productivity would fall. Populations would stress. The bigger problem, as in the Ordovician scenario, would be the biosphere. Phytoplankton in the upper 100 meters of the ocean, where sunlight penetrates, would be damaged by the increased UVB. Many of them might die.
Those that survived would produce less oxygen and less organic matter. Small crustaceans like krill, which feed on phytoplankton, would be reduced. The fish that feed on krill would be reduced. The larger marine mammals and birds that feed on fish would be reduced. The marine food web, which provides a significant fraction of the protein supply for many human cultures, would contract. Terrestrial plants, too, would be damaged. Leaves would photobleak. Photosynthesis would slow. Crop yields would fall. The yields that feed human civilization depend on the efficiency of photosynthesis. Any significant global reduction would have consequences that propagate through food supply chains in ways that are difficult to model. None of this would be fast enough to produce a mass extinction of humans.
Civilization is technologically equipped to buffer itself against many such pressures. We can grow food indoors. We can develop UV-resistant crop varieties. We can apply sunscreens. We can distribute medical care. The human species in particular is unusually resilient. But that resilience is uneven. The poorest parts of the world, the most agriculturally fragile regions, the populations most dependent on subsistence fisheries, would suffer first and worst. A gamma-ray burst attack on the atmosphere would not be a democratic disaster. It would be unevenly distributed, like all other environmental catastrophes. Still, the scenario that ends the human species is not the likely one. The scenarios that cause partial collapse, regional crises, and significant biosphere contraction are more plausible.
In the gravest cases, with a very close burst pointed directly at us, the damage would be enormous. But even then, there would likely be survivors. The Earth, to the astonishment of anyone who examines her, has survived worse. The end, Permian extinction, wiped out roughly 96% of marine species and 70% of terrestrial vertebrate species. The planet still had life afterward. The forms that life took were different. The diversity took tens of millions of years to fully recover. But life continued. A gamma-ray burst, even a direct hit at a close range, is unlikely to do worse than the end. Permian. It is one of many possible disasters, one of many possible pressures on the biosphere, a particularly sharp and dramatic one, but not uniquely catastrophic.
There is in this a small and honest comfort. The universe is violent. The violence is distant. The effects, when they reach us, are filtered through many layers of shielding, both atmospheric and probabilistic. Our survival, up to this point, has not been accidental in the philosophical sense. It has been the predictable outcome of a thin atmosphere, a wide galaxy, and the narrow beams of distant deaths. The thin shell around the Earth is what stands between us and most cosmic violence. It is also what stands between us and ordinary weather, and ordinary cold, and ordinary suffocation in the vacuum of space. The thin shell does everything.
Without it, we would last about a minute and a half before our bodies began to fail in several terrible ways at once. When you breathe in slowly, and then out slowly, in the quiet dark of your room, you are exchanging gases with a shell whose thickness is only a small fraction of the diameter of the planet under you. That shell is, at this very moment, intercepting cosmic rays, deflecting solar protons, absorbing distant gamma rays, shielding you from ultraviolet radiation, and providing you with the precise mixture of nitrogen and oxygen that your body's metabolism evolved to use. Any of this could, in principle, be interrupted.
None of it probably will be, tonight, or for the rest of your life, or for the life of the person next to you. But the improbability is not zero. It is small, but it is not zero. The universe is not indifferent in the sense that it opposes us. It is indifferent in the sense that it does not know we are here. The thin shell does know. The thin shell is us. And even its small knowledge, its physical buffering, is enough. Most nights, anyway. Most nights are enough.
Let us finish with an image that is worth carrying with you as you drift into sleep. Imagine you are standing in a dark place, far from the lights of any city, on a clear night. The sky above you is spangled with stars. You have picked out a few constellations. Perhaps you see Orion, its belt and its shoulder, its sword hanging downward. Perhaps you see Cassiopeia, the lazy W on the northern side of the sky. Perhaps you see the long band of the Milky Way,
The galaxy seen edge on, with its faint patches of dust silhouetted against the brighter stellar crowd. The sky you are seeing is, in a sense, not the present sky.
The light from each star left its source at a different time in the past. The light from the nearest star other than the Sun, Proxima Centauri, takes about 4.2 years to reach you. The light from Betelgeuse, the red supergiant on Orion's shoulder, takes about 500 years. The light from the Andromeda Galaxy, faintly visible to the unaided eye in good conditions, takes about 2.5 million years. When you look at Andromeda, you see it as it was when our ancestors had not yet separated cleanly from the lineage that would become Homo habilis. The sky, in other words, is a collage of times. Every star you see is the past.
Now imagine that somewhere in that collage, perhaps in the band of the Milky Way, perhaps in Andromeda, perhaps in a galaxy too faint to resolve without a telescope, a star is dying. Its core is collapsing. A black hole is forming. Jets are being launched at the speed of light. A gamma-ray burst is beginning. You do not see it. If the burst is in Andromeda, its light will not reach Earth for another 2.5 million years. By the time it arrives, our civilization will be long gone, either evolved into something we cannot predict, or vanished in ways we would not want to contemplate.
The flash will fall on a planet whose inhabitants, if there are any, will have no memory of the people now standing under this sky, looking up, listening to this voice. If the burst is in our own galaxy, perhaps at a distance of several thousand light years, its light will arrive on a human timescale, but still after thousands of years have passed, the people who witness it will not be our contemporaries.
In that case, there would be, before it arrived, no warning. The star would have died. The news would have been in transit for all that intervening time. Its arrival would coincide with our present, the exact present in which you are now listening. It is almost certainly not arriving tonight. The odds are overwhelmingly against it. But it is a strange thing, once you know the facts, to look up at the sky and realize that every single point of light you see is a message already sent. The senders have all, in a sense, already committed themselves. The letters are in transit. Some of them are ordinary letters, saying, "I am still alive, still fusing hydrogen, still shining placidly."
Some of them are dramatic letters saying, "I am near the end of my life. I am burning my last fuels. I may die soon." And a very small number of them statistically are saying, "I am in the final second. I am collapsing. I am sending you my final flash." Most of those final flash messages will never reach you. They are aimed elsewhere. Some of them, however, are passing through the sky every year, every month, every day. The ones that happen to be aimed at Earth are caught by our satellites, and very rarely by our eyes. When you look up at the stars, you are looking at a mailbox that has been receiving deliveries for billions of years. Some of the envelopes have been opened.
Most have not. The mail never stops. It only slows occasionally during a period of cosmic quiet. There is a thought in this that I want to leave you with. The ordinary night sky, the one you have walked under all your life, is not the calm field of diamonds it appears to be. It is a record of endings. Every star will die. Every galaxy, given enough time, will fade. The light that you see now has been produced at the cost of fuel that will not be replenished. The universe, like any system, is running down. It is running down slowly, so slowly that the process is almost indistinguishable from eternity on a human timescale. But it is running down. Most endings are quiet. A star like the sun will, in 5 billion years, expand into a red giant, engulf its inner planets, and slowly shed its outer layers into space. It will leave behind a white dwarf, a small, hot, cooling ember that will last for trillions of years before it too fades. That ending is slow and peaceful. It is not a gamma-ray burst. It is not a catastrophe. It is a long sigh. Some endings are louder. A massive star, 10 or 20 times the mass of the sun, will end in a supernova. Its gamma-ray production will be modest. Its body will be scattered across a parsec of space.
It will leave behind a neutron star, spinning, magnetic, glowing in X-rays and radio waves, for as long as its rotational energy lasts, and a very small number of stars at the upper end of the mass distribution, with the right conditions of rotation and envelope, end in the deaths we have been talking about for the past hour and a half. Their dying flashes are the brightest things the universe knows how to make. Their light is visible across most of the observable cosmos. Their deaths are, in every meaningful sense, the loudest endings physics permits. Tonight, some number of those endings are in progress. We do not know where. We do not know when the news will arrive, if it ever does.
We only know that the universe is arranged in such a way that these endings continue to happen, at a rate of perhaps 1 per galaxy per million years, across all the hundreds of billions of galaxies visible to us. Somewhere in that vast ensemble, always, a star is dying in this way. Always. Right now. Right as you are breathing. You will most likely never see any of it. That is almost certainly for the best. The ones we can see, we see only because they are far enough away that their violence is abstract to us. If we were closer, we would not be able to see them. We would be part of them.
But the fact that they are happening, and that we know they are happening, and that we have traced their mechanisms from Cold War satellites to afterglows to neutron star kisses, is one of the quiet triumphs of our species. We have looked into the darkest corners of the sky and found deaths larger than our planet can even simulate. And we have given those deaths names and equations and expected rates. We do not, in the end, understand most of the universe. We understand enough of it to know what ignorance means.
We understand enough of it to know that every night sky above us is, in some sense, a courtroom of past verdicts, read out at the speed of light, very slowly, into an audience that is learning to listen. Breathe in now, breathe out slowly. The sky above you is busy. It has been busy for all of history. It will continue to be busy for as long as there are stars. You will not, in your lifetime, probably see any of its largest performances. You will not need to. The small, ordinary performances are enough. The blue sky of your mornings, the orange of your evenings, the dark of your nights, the occasional meteor.
The occasional thought, like this one, that takes you out beyond your own body for a moment. Somewhere, a star is dying now in a way that makes the sun look like a candle. Somewhere, a neutron star is falling toward another neutron star, thousands of years from their final touch. Somewhere, a beam of relativistic matter is breaking through the outer atmosphere of a stripped-down giant, and a flash is beginning that will be visible to some distant audience, millions of years from now. You are not that audience. You are a much smaller audience, to a much smaller piece of the performance. You are the audience to your own breath, your own pulse, your own quiet thoughts at the end of a long day.
You are the audience to the warmth of your own body beneath your own blanket. You are the audience to the small, improbable, precious fact that, tonight, the beams have not landed on you. Tonight, the sky has been kind. Tonight, in this one small room on this one small planet, you can close your eyes. You can let the day fall away. You can let the sky do its work above you, at its own scale, without needing to carry any of it on your shoulders. There is nothing you have to do about it. There is nothing you could do about it if you tried. You can simply, gently, rest. The universe will continue. The endings will continue.
The stars will continue to die and to fire their brief beams into the expanding dark. Some of those beams, sooner or later, will find their way to your descendants, and those descendants will make of them whatever sense they can, as we have made what sense we can of the ones that have reached us. And tonight, while all of that goes on, you are here, warm and breathing and safe. And tonight, that is everything. Sleep now. The sky will hold itself together without your help. It always has. Total, 17,540 words, 12 chapters.